you.
Next up is Cian from the University of Bristol. And he'll be talking on probabilistic estimation of correlation matrices from binary spiking data.
Great, thank you. All right, shall I just start? Yeah. Okay, great, thank you. So yeah, I'm based in the University of Bristol, and I'm going to talk about a method for estimating uncertainty around correlation matrices, and particularly from binary data, and I can explain why only binary data later. So first of all, just to motivate, so why should we care about correlations, or why does anybody care about correlations? One answer is that these days, neuroscience has entered like the big data era. So for example, here's a sort of raster plot from Carsten Stringer and Marius Pasatariu when they were in Ken Harris's lab in UCL. Where they've done 2-photon calcium imaging from 10,000 neurons simultaneously in V1 of a mouse as it was looking at some visual stimuli. So you can, if you stare at this for a while, you can see some interesting activity patterns, but then what do you do after that? You know, what do you go from there? And a common step is to, well, we'd like to understand these, and a common step is to compute the pairwise correlations between each individual pair of neurons, and then study that thing. So for example, you could try and do PCA on it, or ask how the correlations change with stimulus condition, things like that. So they're just like, I see them as a window into what neural circuits are doing and give us some clue about the neural code. Hopefully that we can relate to some theories, so some theoretical modeling about what the parts of the brain are doing. So what is a correlation, or what do correlation matrices look like? Here's an example. This is from the same data set that they've released online. So it's just...
We only see your title slide at the moment. I'm not exactly sure if your screen sharing is working correctly.
Oh, sorry about that. Maybe I need to, let me try and just share my desktop. That's weird because it was advancing for me. Okay, let's try this. Does that work now?
Yes, much better.
Great, okay. Then I'll just quickly show what I was talking about. This is the 10,000 neurons raster. Thank you for the clarification, Elenor. I would have just kept talking. 10,000 neurons from mouse V1. So you can see some interesting structure here, but often people will measure the correlations as the object of study to try and get some insight into what's going on, because just staring at this is not going to get you too far. And here's an example of a correlation matrix taken, I computed from that data that they've released online. And it's just 40 neurons in this case, so for random 40 neuron subset. And typically, this is pretty typical of what you get if you measure correlation matrices in most brain regions, where with calcium imaging or electrical recordings, you see that a lot of the values are close to zero, some positive, some negative. On average, at least within a local region, neurons tend to be slightly positively correlated on average. So the mean is probably like 2 or 5%, something like that. But there's, if you squint at these things, you see some structure in there, and we try and interpret that structure. So what's the issue? So people do this all day, every day. Why do I think it's a problem, or what do I think the issues are? So given a sample correlation matrix, kind of open, or issues that people don't often worry about that I think are important are, we might want to ask a question like, is any given element of that matrix statistically different from zero? So this, if we compare the correlation between neuron 16 and neuron 8 or whatever that's in this element, is that number, like if it was 0.03, is that statistically different from zero or not? That's one question we might want to ask. And people often do ask that as a kind of way of thresholding these correlation matrices, or as in the last talk, we saw examples of people trying to use them to infer connectivity between neurons. We might want to ask, take two correlation matrices from two different conditions or two different ages of an animal or something, and ask if they're statistically different, or what's the distance between them. And then there's more technical questions we can get with downstream analyses. If we're in a situation where the number of neurons, this is the wrong way around. If the number of data points is less than the number of neurons that we've recorded from, we get a correlation matrix becomes a low rank. And that could mess up downstream analyses, like for interpreting the output of PCA or something like that. And that's getting to be an issue now. So for example, those 10,000 neurons, I think they were recorded at about 2 hertz. So you would, every hour, you would get about, I'm going to get this right, 7,000-ish samples in an hour. So if you record it continuously for 1 hour and you're 10,000 neurons, you still wouldn't be at the point where you had more samples than numbers of neurons. So that's a problem we'd like to fix. So my answer to this, and not just mine, but an answer to this is to treat it as a probabilistic problem where we put uncertainty on all the numbers in the correlation matrix and then use that to address these questions or fix these questions maybe. So going through the basic idea, first of all, I'm going to assume that the spiking data is binary. And if you had calcium imaging data, you could get that by thresholding the fluorescence values. So everything above some value is 1, everything below it's some 0. That's not uncommon. Or it might be the output of a spike inference algorithm that people apply to the calcium imaging data. For electrophysiology, a common way to generate binary data from spiking is to discretize time and then ask if the neurons spiked or didn't spike. And usually people take very small time bins, like 10 milliseconds, where the likelihood of 2 spikes is small. So most of the time we see 0, 0, 0, occasionally see a spike. So if we get in that situation where we've got a binary spike train, then if we think of 2 neurons here and time along this x-axis, this is when neuron 1 spiked, neuron 2 spiked, they both spiked this time bin, and so on. Then the trick is going to be convert that to some sort of binary sequence. So there's a 1 where there's a spike and a 0 where there's no spike. So at every time point, we've got a pair of values, 1, 0, 0, 0, 1, 0, or 0, 1, 0, 0, and so on. And now if we think for 2 neurons, if they're both binary, then there's only 4 possible configurations, 0, 0, 1, 0, 0, 1, and 1, 1. So what we can do is count how many times we observe each of those patterns, those binary patterns. And in this case, we've got 29 0, 0s, 6 1 0s, 3 and 2 of the other 2 patterns. And this is, again, pretty typical. A lot of the time, neurons are silent. So we often see more zeros than that. Okay, and then after that, if we assume that the data, now this is where we make some assumptions, we're going to treat this as thinking about each of these binary pair of binary numbers as a pattern. And like I said, there's 4 possible patterns. So we think of those as samples from a discrete distribution with 4 states. Then the likelihood of observing any set of counts, like the ones we've just figured out here, is given by the multinomial distribution. So that's just the probability of observing that pattern. And the k's are the counts, so that's going to be our data. And the parameters of this distribution are the probabilities of the 4 numbers. So the sort of true probability of observing each of the 4 patterns. And in this case, that distribution has just 3 free parameters because we know that the sum of these 4 probabilities has to add up to 1. So it gives us a constraint. If we know that, and that, we can figure out the final one just by subtracting them from 1. So after that, if we assume some prior probability distribution, this is following a Bayesian model, prior probability distribution over these 4 probabilities here. And we can get the posterior distribution over the 4 probabilities given the observed counts. And the trick now is we don't really care about these directly, usually. What we're more interested in is the pairwise correlation between the pair and the 2 individual neuron firing rates or firing probabilities on average. And in this case, there's a unique mapping from any possible configuration of these 4 probabilities to the sort of marginal probability of neuron 1 firing, or the firing rate of neuron 1, the firing rate of neuron 2, and the pairwise correlation between the 2. So we can just sort of directly write that down given these 4 numbers. And that means that if we if we have a method for sampling from this posterior distribution, which is fairly straightforward using Markov chain Monte Carlo methods, then we can transform those samples and get samples from the sort of marginal distributions for each of these 3 things. So now we can get joint sort of samples from the joint posterior over these three things. And that's kind of what we're after. So how does that work? If I simulated some pair of binary neurons, and imagine they just collected 1 second of data, 1 minute of data, 1 hour of data in 10 millisecond bins, and then asked what was the posterior distribution over the pairwise correlation in each case. And the true value I had set to, I think, 5%. You can see that dashed line here. If we only record for 1 second, the posterior distribution over the correlation is very broad, as we might expect, reflecting our big uncertainty. It could have been that that data came from an underlying correlation of 0.4 or even minus 0.1, something like that. We're not sure. We have 1 minute of data that gets a lot tighter, converges on the true value, but you'll notice even the peak is not aligned with the true value, so there's some sort of random error in that case. But with loads and loads of data, like 1 hour of data, then the posterior distribution converges to like a narrow spike on the true value. And then the next thing, again, we can not only get these sort of probability distribution over the correlation, but because we have the joint samples from all three parameters, we can plot them here. So we've got these three marginal distributions for each parameter, but we also got, here I've plotted kind of a heat map of the samples for each pair of parameters. So the correlation and firing rate of neuron 1, correlation firing rate of neuron 2, and the firing rate of both neurons together. So that's great. So now we can do things like ask if that correlation is statistically different from 0. So for example, thank you, how much of that mass is a certain distance away from 0 or crosses 0. In the red case, there might be a little tail that crosses 0. In the green case, we're almost certain it's not 0. In the blue case, we don't know, but we can put a number on that. So it's a fairly systematic way to assess that. So what do we do with more neurons? We have to, the issue is we can't sample from the true underlying distribution like we did in the 2 neuron case, because the number of possible states scales exponentially with the number of neurons. So we've got 100 neurons, we've got 2 to the power of 100 possible states, and that's just computationally intractable. So the trick I'm going to propose, and just almost finish on that, is to approximate that full posterior distribution with a multivariate Gaussian. So we assume there's some latent multivariate Gaussian distribution. Okay, I'll finish now. Thank you. Some latent multivariate Gaussian that we're trying to estimate all these parameters over given the data. And so here's one example where simulated data from 10 neurons and drew samples from the posterior. And the nice thing is there's relationships between each pair of values in this that reflect their joint dependencies in the posterior distribution. So again, we can use that to ask questions like, are these two correlation matrices different from each other? So finishing, there's still some issues I need to solve, which are, it doesn't scale well, need to figure out how to solve that. I need to come up with a way to guarantee the samples are from valid correlation matrices and how to handle the prior in a principled way. Thanks, and sorry for running over time.
Thank you very much. Cian, I'll leave it straight to the questions. We have a question already in the Q&A. Sean, I've allowed for you to talk, so you could ask your question live if you want to.
Hi. I think you may have somewhat mentioned it actually in your final slide, but I was just wondering about the prior that you use for the Bayesian analysis.
Well, I think in the example I used a flat prior over those 4 states, but
sure.
The tricky thing is we'd like to maybe set priors on the correlations directly, and then for the sampling we'd have to sort of back transform those to ask what prior they imply over the underlying states. So that's not too hard in the 2 neuron case. For the full correlation matrix, it's tricky to know what to take, but there are some standard prior distributions over covariance matrices that we could use, but I haven't coded up, I should say.
Yeah, great.
Thank you very much. The next question is from John. John, I've also unmuted you. You could ask your question now.
I was just wondering, you're assuming that the spikes are perfectly aligned, but there can be a delay or some variability in that. How would you include that in your model? That's a good question. It's not in the model at the moment. So if you shuffled all the time points here, you would get the exact same results. It's ignoring time. And that's not uncommon for most types of analysis, including like when people do PCA. Maybe you could have a model that knows about time dependencies. So some sort of Markov underlying model for the dynamics of the spike trains.
but I haven't considered that yet. But it's very difficult. Just explodes the state space even more.
Yeah, no, I could imagine.
Thank you very much. We are having loads of questions come in. We have time for one more brief answer. This is from Mark. I'm just allowing you to talk as well. Brief answer, please, and the rest, Cian, please answer in the chat later or in the Q&A function.
Thank you. So, Cian, I was pleased that you were trying to address the realistic case where you have many neurons. We often look for some sort of multivariate structure in the form of eigenvectors. How close are your eigenvectors from your multivariate model to the underlying true values?
Oh, that's a good question. I mean, in the limit of infinite data, it's going to converge. We know that's true. And all I'm doing here is matching sort of moments of that final distribution. And your question is like, how good a model is the multivariate Gaussian? And that's just going to depend on the data. I don't know. It depends on the type of structure we get in the data. If there's higher order correlations between triplets and quadruplets of neurons, then it's probably going to start becoming a bad approximation. Mm-hmm. Or maybe we can fix that in the transform as well between the multivariate and the final covariance matrix. But that's a problem I haven't really figured out yet. Thank you.
Okay, good.
Thank you very much, Cian. Thank you again for